Hoekom? Daar's die video. Daar's hy. Ag, dames en here, ladies and gentlemen. Okay. I have had 2 questions about the project, and these are important questions. So, the first one is fairly easy. There is an unsort button for which you get a mark on the GUI, right? So what does it mean? Basically, if you click on that button, you should randomly shuffle your input again so that you can resort. Okay, that is acceptable. I'll take that as a correct implementation. The other option is just read the original input file again during the demo, meneer Sillier.
I think an unsort button, but if you just repick the method, it already unsorts it from the original file, it rereads it, and then...
So it's a silly mark on the marking scheme. So when you go for the demo, you explain to the demi what your unsort button does. As long as it does not try to sort the sorted data again, I'm happy. Does that make sense? Yeah. Yeah, so what I don't want to do really is, even if you do a random shuffle again, you should, actually what I want to compare is 2 different algorithms on exactly the same input data, right? Which you would achieve if you read again from the file, okay? But that button is sort of ambiguous, and that is all Lodewijk's fault. Let's blame him, he's not here. Because he implemented all the projects over the holidays, and one of his briefs was find things that are ambiguous, that do not make sense in the project, and he missed this one. Okay. So I will tell the demis for that mark on the marking scheme, the unsort button, just ask the student how they did this and what happens. Okay, right, so it's basically 1 mark for free, yay! The other thing is the memory. So what Lodewijk did over the holidays is he ran an algorithm, measured the memory, yippee-yay, it works. But the moment you start using this measuring of memory in earnest, it all breaks down, it doesn't make sense. So again, as far as memory is sent out an email yesterday, Saturday, you have to have the theoretical analysis on your report, right? Draw the picture so that you remember it. But I'm not sure whether during the demo it will make sense for us to watch your memory usage, because there may be junk. Okay, so we'll handle it as it comes. It's sort of a lot of marks, so I'm considering not marking the practical part of the memory management. So leave it there if you did implement it. Don't try to take it out and change your project now. But we won't penalize you during the demo if you get junk answers there. Does that seem fair? Okay. Right, meneer Sillier.
When it has to read a file, I just wrote my own files. Is that fine?
You just what?
I wrote my own files for small, medium, and large input.
We're going to have other files. So you have to read the file name somewhere.
How do you do that with standard raw?
Okay, send an email to Lodewijk just to assist on that one. Okay. I'm not exactly sure how he's going. We can rename our input files to your file names. Would that make sense? That's fine. It will work.
Does it also have to handle the Python, or can it just read according to the file name?
Does it also have to handle?
The Python.
I don't know. What did Lodewijk say? Do you need input piping? He gave a template and APIs and stuff. I don't know. Send an email to Lodewijk. Put it on the forum. Yeah, put it on the forum. More questions about the project? Yes, quiet. You do have the test cases? Where are the test cases? You have example test cases. We will have similar test cases to use during the demo. So you don't get the demo test cases beforehand, but you get sample test cases which will be similar. Yeah? More questions? Yes. Put it on the forum. I don't know. Lodewijk watches that forum like a hawk. So if you have a question, the question now was what would be the size of the medium and the large input files for the test cases? I don't know. He set it up. So put the question on the forum just to make sure. More? Okay. Is everybody sure their get works? Yeah, your get has got to work. You must, yeah, vraag. Andrew Colette, after the lecture, toodle up to him. Do you know where his office is? You go out here, you follow my direction. Turn left towards the engineering complex. There's a set of stairs next to the lift. Go up the stairs 1 floor. Then you are in computer science. You walk into computer, no, now my direction is wrong. Okay, you walk into computer science. There's only one way, and then you get a kind of T. You walk in from the lift, you turn to your left, and the very large office, very last, very small office in the corner is Andrew's. Okay. If he's not there now, then send him an email. He's sort of 10 o'clock, he should be in. We're not early people. Yeah, he should be in then. Okay. Right. Anybody else with Git problems? Right. Cool. Okay. You cannot be late with your project ending. Please try from a half an hour before the deadline, start trying to submit. If you're late, you're late, you're dead, you die. Yeah? Try from half an hour before the deadline. Please. Yes? Cool. Okay. So, throughout the course of, throughout the course, I will periodically ask you if things are still going well, because we have a formal student feedback session in the beginning of the second term, but that's too late if I'm doing something that you really hate. So could you please give me some feedback now, if you have, on what can I do better? So my questions are, does it work for you not to have slides? Does it work that I work from the book? There's a yes. Yeah, people are okay with that. Cool. The way the projects are structured structured? Do you get enough help from the demis? I know projects are always, you know, wow, this doesn't work, and there's a bit of anxiety towards the end. But you feel capable of handling the project with enough effort from your side. Yeah, you're happy with the projects. Something that we can change, that we can do better. Remember, Lodewijk will be there tomorrow night, yeah, 7 to 9, if you have any last minute disasters. The volume of work is somewhat high. Indeed, it is. But I do try to point out exactly how you should learn, what you should know. Given the high volume of work that we have to cover in the curriculum, do these regular tests, do they work? I particularly like the idea that I do a chapter, I learn that chapter, I finish. Yes? Instead of having 2 opportunities, and if my boyfriend just broke up with me during the semester test, and then I got flu during the exam, I basically have to repeat the course. So I like, personally, I would have, it's more work for me, right? But personally, I would have liked as a student to have more regular tests. Also, it gives you a break during the proper sort of wild time frame where all the semester tests take place, because then you don't have the CS to worry about anyway, because we're not using that opportunity. Okay. However, if you want to tell me you have if you tell me you don't prefer this, then we can, yeah? So is there anybody who does not want to keep this method of working? I don't know all your names yet, so if you put up your hand and say no, I'll probably will have to go back to your first year pictures, which are unrecognizable anyway. Yeah, so is everybody still happy? If you're not, please tell me. If you don't want to tell me to my face, then tell Miss Kutsia to come to me with a, look, this is not working for us. Okay? And I fixed the weather, so it's not so hot in this room. Right? Please, 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 if at any stage you feel that I can change something, I'm very adaptable. So really, just shout. And then the last question, is this still, are you still learning something? Okay. You're so nice. You're a bloody nice group. I like you. Okay. Seriously, you get some groups who complain about everything, but even the demis on Friday told me this is such a nice group. They come in and instead of saying, oh, what should I do? They say, I tried this and this and this and it doesn't work. How should one do this? So cool, keep up. And I would honestly, how many of you are not going to take Computer Science 3? Yay! Okay, I want to pull all 47 of you through to Computer Science 3 if possible. Yay! Okay. Because it becomes even more fun next year. Okay. Right. Binary search trees. I know you did this last year, and I thought this is perfect because most of you are thinking about the project rather than new work. So let's look at the binary search trees in some detail today. We finish it. And then on Wednesday, you have to be here because it's 20, what's the time when you hand it? 4 o'clock.
No, on the website it says 16.
Yeah, on the website it says 60.
I should have made it 10 o'clock. Anyway, no, I'm not. No, you can always extend, but you shouldn't shorten it down. That's me.
Sorry,
Oh, okay. So binary search trees, I think you basically know how to do the Java because you did it last year. So you know how to implement a binary search tree, and roughly you know what the problems are when you use a binary search tree to do searches. So we are going to add a few little some of them quite tricky methods to the binary search tree so that we can use it decently for sorting. Searching, I'm marking, so sorting is the thing in my head. Okay, so let's just get, again, the formal definition of a binary search tree. Binary search tree is a binary tree where each node has a key and a value and satisfies the restriction that the key in any node is larger than the keys to the left and smaller than the keys to the right. Yeah? In other words, picture, there we go. This is a binary search tree because if you look at any given node, for example, E, the subtree, all the nodes in the subtree to the left of E have keys smaller than E. All the nodes in the subtree to the right of E has keys larger than E. Okay, so as long as that's fixed, then we're happy. This is different from the heap, right? Right. So same idea as the heap implementation, but a different restriction. So going to the left, I go smaller. Going to the right, I go larger. Always. Okay. The other thing that we will do, which I think you did not do last year, is we are going to keep count. At each node, the algorithms keep count of how many nodes in my subtrees, right? So if I look at X, I'm the only node in this subtree, so my count is 1. All the leaf nodes, yes? You know what a leaf node is? All the leaf nodes will have count 1. Then we look at something like A, and it has count 2 because in this subtree there are 2 nodes. E is 6 because 1, 2, 3, 4, 5, 6. Yes? I'm not going to say anything about it. This is the reading the algorithm, checking for myself. What do I do if I get duplicate values? Remember where this comes from? Search example. Yeah. So search example has 3 E's and 2 A's. Yes. We don't store duplicate values of nodes in the algorithms as presented in the textbook. You could decide to have it. Yes? But the algorithms in the textbook work on unique key values in the binary tree. The thing is then, what do we do if we get duplicate values in the inputs? Right, go, and that is self-study. Wow, very difficult. I'm not even going to look at the code because this is all from last year, how to get a value, yes, in a binary search tree. Well, let's just look at the example because clearly you know how to do this. Am I correct? You did this last year, how to search for a value in a binary search tree. Ja? Ja, okay. Right. So let's search for R. R is the value I'm searching for. I start at the root. R is less than S. Therefore, I have to go left. I get to E. R is bigger than E. I have to go to the right. And yippee yay, I got a search hit. Yes. Remember that the average height of the binary search tree, if it's nicely balanced, the height is, if I have n nodes, my height is log n. If the binary search tree, if the binary search tree, yeah, the sound is unusable if I don't stand here, but I like walking around. So if a binary search tree is totally unbalanced, what is the depth of the binary search tree? N, right? Because then I get sort of this default thing. And in which case, what must my input data look like so that I get it totally unbalanced? Sorted, right. And if it's reverse sorted, it will just go, the same thing, it will just go to the right, okay? So what I want is nice random data, and hopefully, on average, I'll get a nicely balanced tree, okay? Good. When do I know that a node is not in the tree? I'm searching for something. Let's look at an unsuccessful search. Well, this is stupid, a voorbeeld, but okay. So here we're searching for a T. It's not in my tree. T is larger than S, so I go to the right. I look at this subtree. T is less than X, but X does not have any choice. T is not in the tree, right? So it's, if you hit the null link, you're comparing, going left, going right at each compare, and then when you get to a null, it's a search miss. Alles baie maklik. Okay. Inserting into a binary search tree. Oh, what do we want to insert here? They want to insert an L into our standard tree. Do the same thing recursively. L is less than S. L is larger than E. L is less than R. L is L. Larger than H. It's less than M. Yippee! I always insert at a leaf. Does that make sense? I always insert at a leaf, so I get to a point where there's a node with a null link, and I just set that link to the node I want to insert. Very easy, no problems whatsoever. How would you keep count? And why do we want to keep count? I'll forget a copy. It is possible in our API to ask questions like, what is the minimum value in my tree? How do I find that? You just bugger down the left branch, yeah, until you hit a null, and then you know this node with the null to the left, that node is my minimum. The maximum, you do that to the right. But to answer any form, any question about rank or range, what does that mean? Rank or range is for a given node, its rank would be whereabouts does it fit into my data set from a sorted point of view. So is this the 5th largest? Is this the 3rd smallest? That kind of question. That tells me about rank. Do you know why you would have been a multi-billionaire if you started Google? Simply because of something called rank. Yes? At Stanford, the two guys who started Google didn't simply do a web search. They ranked the pages. The PhD for, I can't remember which one of the two. His PhD was called PageRank. That was the algorithm, the PageRank algorithm. So he devised a sort of clever algorithm which said, if somebody types in this search string, the pages I'm going to give you back will be the most relevant pages. So their rank in the order of relevance would be highest, second highest, and so on. Yes? And if you think about it, if you search on Google these days, you probably seldom would you continue to the next page. Yeah, you mostly find your answers on the first page. So that is worth gazillions to somebody who wants their answers on the first page. Okay. Especially on scholar.google.com. If I type in my surname, I want all my articles there, not somebody else called van Zyl. Right? It's worth something to people to be cited, for companies if you have ads, to have your things come up first. Okay. So how given a binary search tree, how do I know which is the third largest? Unless I go through the whole damn binary tree and I say, well, this is the largest, so it's not this one. Then I want to backtrack, but remember, you can't backtrack in a binary tree. You don't have links pointing upwards, you only go down. So that's a bit of a mess. But there's a very easy solution, is you give a value to each node as you insert it. Okay? So you're basically counting the nodes. If I know how many nodes are in my subtrees, I can use that count to find the range and the rank. Okay? Right. So you will keep count. If you look through the algorithms, please make sure that you follow how they keep count of a given value, of the value at a given node. Okay? Right. Ag, Jessie, ek wonder of ek eers dit wil doen, maar okay. Juffrou Coetzee, proposition C for the test. Yay. Be very careful with this one. In the proposition it says, search hits built from n random keys require 2 ln n, which is about 1.39 log n. Yes, compares. So it's searching. What is the cost model for searching? We said last week, Wednesday is a long time ago, but last week, Wednesday, we said, what do I do when I search? I compare. Am I at the right one? Am I not? So my cost model is compare, so I'm going to count the compares. So you build up your compares. What you want to know about is what is the longest path I can follow through the tree. Okay. So you build up again a recurrence relation. Yes. And note that they work this on the average. So the crux of the recurrence relation over here, if I let Cn be the internal path length of a BST, what is the internal path length of a BST? It's the length of all the paths added. The sum of the lengths of all the paths is the internal path length. Okay. And then random insertions. So the average cost then gives me the path length divided by n. We're working on average here, not best, not worst, average. Okay. So once I have the path length, I know how many compares I will make on average. And then we build up again a recurrence relation. So I have my Cn, you start with your start, C0 plus Cn minus 1 divided by n plus C1 plus Cn minus 2 divided by n and so forth. Be very careful. That is wrong. 2 ln n, not 2 n ln n. If you think about this problem, we're starting with 2 ln n, but what they're doing over here in the book, they say to solve this recurrence relation, I'm going to solve it similarly to the proof in section 2.3, which gave me an n ln n, but it was a slightly different recurrence relation in section 2.3. Yeah.
Isn't the internal path length always n if it's the length to all the ends? Is it the sum of them or is it just the longest?
Moet ek myself nou verspreek? Adding the depths of all the nodes. No, you're adding the depths of all the nodes. So that will not be the number of nodes. It will be the depths of all the nodes. Yeah? Good. Thanks for the question. All right. So just be very careful over here. In section 2.3, there's a slightly different recurrence relation, which approximates to 2n ln n. But the method used in section 2.3, if you apply that method to this slightly different recurrence relation, you get 2 ln n without the n. So it's not a typo in the book. They're just referring you to the method. And for this specific recurrence relation, you get 2 ln n, not with the n. Okay. Right. But it's your gut feeling should tell you that if you have a nicely random binary search tree, I'm sort of getting to log n, right? Because of the mathematics, I get to ln n, yes, which is approximately 1.39 log n. Okay, on average. Okay. You know how to insert. You know how to search. Did you do deletions last year? How to delete from a binary search tree? Keeping the order. Yes, ek kan wonder so min van julle weer gekom. Okay. I was not sure if any did that with you. Okay. Right, so rank is fairly easy. As I insert nodes, I keep a count of my values. Okay? Now, the key of rank 3, let's make sure that we understand exactly what we mean by rank in this context. If I ask you, give me the key so that precisely k other keys are smaller than that one. Yes? So if I ask for the key of rank 3, then 3 other nodes must be smaller. You see, nou probeer ek het oorsit, maar okay, what does that mean? I'm the 4th smallest? Yes? Yeah. So that is what I mean by rank. The keys such that precisely k other keys are smaller. And it seems to be pretty straightforward if you use the count, but it's not. So if you can do deletions, I'm not even going to look at the algorithm. It's just a question of connecting up correctly. I'm going to concentrate on the rank then. Let's consider the search example. And if this is my example input tree, and I want the node such that there are exactly 3 other nodes smaller. Well, there are many nodes smaller than S. It's not E, because E has 2 nodes smaller than S. R has 1, 2, 3, 4, 5 nodes smaller than it's not R. And yippee, it's H. Okay, let's look at this again. If I want to find the node such that exactly 3 nodes is smaller than it, well, H is in the alphabet such that A, C, and E is less than H, right? So there are 3 nodes smaller than H. But this doesn't look like an algorithm that I can follow. How on earth did I get to H? I did go to the left because if you want to find the rank, it's asking how many nodes are smaller. If you say smaller, I want to go left because this is a binary search tree. So I can go to the left and get this every, yes. But then somehow I had to go to the right again and then to the left again. So this is not an obvious algorithm. Works follows. Remember that the numbers, the count that I keep here are, these numbers, the count, represents the size of a subtree. If I have the size of a subtree, and I know that subtrees to my left is less and subtrees to my right is larger, I can use that to somehow maybe get to the rank. And it is easy as long as I keep moving to the left. So let's try in the beginning, well, the number of nodes in the subtree for S is 8, yeah, because there are 8 nodes in the tree and this is the root. So 8 is larger than my rank of 3 that I'm looking for, so I want to make that 8 less, so I move to the left. At E with 6 nodes in it, which is still larger than 3. Then I move to the left again, but now I find a subtree node is unfortunately less than the rank, so the count is less than the rank. If the count is less than the rank, and I'm looking for a larger rank, that means I can use this left subtree, but I must also go find some nodes in the right subtree. Does that make sense? So I'm getting here A, this, which is less than 3. So I can use these, yes, but I need more nodes. Now the best place to find more nodes is to look at the right subtree of my parent. And then I go down and left as quickly as possible to find which nodes will fulfill this requirement. Okay, so if you think about it carefully, I find these two which are less, yes, than 3. So I have to go to my right, but you do this carefully. We look recursively for the key of rank k minus t minus 1. Where do we come from k? K is the rank I'm looking for, yes? T is what I found there, the 2. So I subtract the 2 from my original value because I already found 2, yes? So now I just want 1 more, okay? So you go recursively to your right and look at the subtree of rank k minus t minus 1. So you look for a subtree with rank 0. Yeah? So at E, I move to the right, looking for a subtree of that size. Since looking for the subtree involves going to the left, I do go to the left. And I find my 2 there, so I have 2 keys in the left subtree, so I'm searching for the key of rank 0 on the left, yes, because now 2 is larger than 0. So I have to go left again. And since H has no children, the left, so I found H. Shall we go through that again? Okay, so I want to find a key of a certain rank k. What does that mean? There are k other keys smaller than this one. Since I'm looking for keys smaller than, I move down the tree to the left. I look at the size of this for each node. Each node is the root of a subtree. And the count of that node gives me the size of that subtree. So in the beginning, the count at S is 8. Too much. I'm looking for 3. So I move to, it's 6. It's still larger than the rank 3 I'm looking for. Therefore, I move to the left. Then I get a value which is less than k. The moment I get a value which is less than k, I know I found part of my solution. Yes? Because both A and C are less than my answer. A and C are sort of my first two nodes that I find that are at the bottom of the I'm looking for the key with the such that 3 others are less than it. Okay, so here I find 2 values at the bottom of my tree. So those must be the smallest because I went to the left. So I found 2 keys that are very small. But now I want to add more keys, right? Because I want the key so that 3 values are less than it, not 2. Okay, so I have my 2, and once I find my 2, I fall back recursively to my root. Yes. And now, since I already have 2, and I have my root, yes, take my value k, subtract this count 2, subtract the first there, so we get 1, which is 0. So on the right-hand side, I'm now for the node of rank 0. Okay? The node such that no other nodes are less than that one. Well, that simply means go to the left until you hit a null. Yes? Why does it work? Look at this. If I get to a rank that is a count that is less than my desired rank, I count those two, A and C. I count the parent, yes, and then I go to the rank 0 and I find H. I think it's cool. You have to read through it 2 or 3 times and do a few examples, but then it starts making sense. Okay? Right, deleting the minimum, deleting the maximum. I'm not even going to talk about it. You know how to delete nodes if you have lots of children. If you have one child, it's easy. Yes, you did this last year? Ja, ek kry 'n paar jaars, so dis cool. Right, range queries, more of the same. And there we are. Important. On page 414, please, please, please. This table is important. Yes, it gives you the summarized version of how the binary search tree compares to the ordered array and the unordered linked list. Okay? You have to know this. And you have to know proposition C. Thank you. I'll see you Wednesday at 12. If there are any worries about the project, please put it on the forum. Lodewijk watches it like a hawk. Okay, great. Thank you very much.